Halogenation, we're adding a halogen to the situation. Again, it's an alkene addition reaction. Kind of picking up where we had left off. I'm just going to go ahead and draw it there. It's pi bond. It's kind of hard to draw on this pen, so give me some credit here. And this is going to react with 2 halogens there. A diatomic, so you know, diatomic chloride or diatomic chlorine, sorry. And what we get is 2 halogens attached to it. And so let's go ahead and go over, that's our overall big picture type of a thing. That's what we're starting with. That's what we put in. That's what we've got. And let's go ahead and just kind of draw the mechanism, the in-between steps here. So we have ourselves one of these things here, a cycloalkene. And here's our halogen, our pair of halogen. Generally speaking, this is going to be with Br2, Cl2. And that's about it. That's pretty much all you're going to work with in this chapter. But I'll use it in white. So remember that, you know, the electrons are never in one place. We're exhibiting dipole-dipole interactions here. So at any given point, this end is slightly positive, and this end is slightly negative. That's not the best of drawings, but I think you're getting my point. So this pi bond here is going to be attracted. It's very similar to electrons here. Okay, so this pi bond here is going to come out and be attracted to the partially positive end of our diatomic, whatever it is we're working with, whether that be bromine or chlorine. And it's kind of interesting to me that once it comes out here, once it reaches up and attaches it here, it senses it. It senses that we're starting to form a carbocation over here. And what it does is it sends it back. It goes back into that direction. But I don't want you to be, I guess, distracted by that, and don't forget that when you have this reaction here, you have this going here and this going here, and this is a general reaction mechanism. The only difference is that we don't form a carbocation. We start to form a carbocation, but this is going to swing back down there and attach itself to there. So what we get is, I'll go ahead and draw this here, we get one of these things. We get not correct drawing there. I'm sorry, I am losing my edge, I suppose you could say. Strained 3-membered ring that is positively charged and negatively charged nucleophile. And so I guess the point that I want to say is we're forming a strained 3-membered ring. So this is our rate limiting step. And because of this strained 3-membered ring, you should be predicting, at least to some extent, the stereochemistry of these type of reactions. And so after that, we have our nucleophile attack, which is really, really fast, comes in and attacks, and it opens it up, and our final product is, in blue, I mean, it's right here, but I'll just go ahead and draw it again to show that it's all part of the same mechanisms here. X and X. Cool. So, what are I guess the things that we need to consider because of the strain 3? I'll just go ahead and talk about this with the halogenation here. That because of the strained 3-person ring, 3-membered ring here that we just drew with the X there, the positive charge there. Because of that, the stereochemistry of every single one of these reactions is always going to be, hopefully this drives home my point, always anti-configuration. Always, 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 always. So with that anti-configuration, what we get is enantiomers. And along with that, we come racemic mixtures. So we started off with an achiral molecule, and at the end we have 2 enantiomers which cancel each other out in terms of chirality, but that's not really something that I want you to focus on so much. Okay, so moving on. Halohydrinformation. So we're adding, if you were to guess, a halogen and then a hydrogen formation. The word origin here isn't as helpful as I had hoped it to have been, but I'll just go ahead and do like we've always drawn. Here's our overall reaction here. of an alkene. And I'm just gonna, yeah, I should have done this in the past ones. I don't know why I didn't include variable of or uneven substitution between the two. There. And I'll explain what I'm drawing here in a sec. Here. And I guess I'll go ahead and show our reactants. So we have a H2O in concentrations here, and we have X2. And so what our end result, our end products is going to be an X and an OH. Yeah, hopefully that looks kind of weird to you, because it looks weird to me. Because we have X2 and we have water. So like every other reaction that we've talked about, these are concentration dependent reactions. And in this we have a very, very large concentration of water compared to the concentration of whatever halogen you're working with, probably bromine or chlorine. So let's just go ahead and draw ourselves the overall reaction. So keeping in mind when you're going through these, the stereochemical effects of it and the rate limiting steps. So like just when we were talking about halogenation, the rate limiting step of this is going to be formation of a three-membered ring. So I'll see if I can't draw that, and I'll go with red here. So I'm just tired of drawing X. I'm going to draw chlorines. Chlorine here, there's slightly positive end there, positive end there, slightly negative end over there. And just like before, my bond is attracted to that. This is going to go off here. It wants to start to form a carbocation, but lo and behold, we're going to have that chlorine is going to come back down to Earth and forming us a blue. So this is our rate limiting, is a 3-ring. Rate limiting step is always going to be the 3-ring formation there. So, see, I should switch colors eventually. There. There, switching to red. We have ourselves a chlorine, positively charged, and a chlorine anion floating around, but we have more water concentration than we do of chlorine. And I'm just going to go ahead and draw this in a large size to, I guess, drive home my point that I'm trying to make here, is that what we have is H2O in larger concentrations than what we have of that Cl anion being formed. And this is so confusing to me. This took me forever to figure out, I guess to really understand, is that OH, this nucleophile, this is completely counterintuitive to me, that it's going to attack at the most hindered position. What the hell? And so what we get is, in our next blue, where are you? Our next step, what we get is this intermediate, not as an intermediate, as the next step. There. I'll switch to white. OH2, which has a positive formal charge, and ourselves a chlorine there. So it went to the most substituted side. That's so weird to me. And since we have such a high concentration of water, do this in white. OH2, drawing it like this so you can see the lone pair reactions. Because we have such a high concentration of water, this is going to attack here, one of the hydrogens there, forming hydronium, thus giving us our, I'll do it in green, gives us our final product here, and a hydronium ion that will be reacting in equilibrium with water, and then the Cl minus as our final products of those reactions. But this is weird. That's weird to me, at least whenever I think about that. So in Halohydrinformation, we'll talk about the stereochemistry. Well, okay, I'll just go ahead and branch off here that we have, because we have a strain, so we have a 3-membered ring. That 3-membered ring has 2 consequences, has stereochemical consequences, and it has kinetic consequences of being the rate limiting step, is making one of those. And the stereochemical stereochemistry, I'm going to switch to white, the stereochemistry of that and the rate limiting step of that three-membered ring. It's always going to be, you guessed it, anti, and the rate limiting step is because of that. But let's talk about some other weird things here. So in this reaction here, because we have such a high concentration of water, chlorine is not our nucleophile. Cl is not a nucleophile. The nucleophile is H2O. H2O equals our nucleophile because it's in such a high concentration. And that's so weird to me because what it does is it's going to, switching to blue, it's going to do a nucleophilic attack. And this is really kind of confusing here. I'll go ahead and draw this here that this, I'll just say H2O attacks. It's a nucleophile. Attacks at it attacks at the most substituted carbon. That's crazy to me whenever you think about that. It attacks the most substituted carbon. And then, because, and hopefully that's not too weird to you, because going back to, we're not forming a carbocation, but we are kind of semi-forming a carbocation. Not necessarily that, but think about that in terms of kinetics of what's the more stable transition states. The chlorine, or the halogen in this context, is kind of like a hydrogen when we were talking about the reactions that we had first discussed. So in this context here, the chlorine is not a nucleophile. The chlorine, or the halogen, is bonded to the least substituted carbon. That, to me, that just, what the hell? That's so confusing to me, at least. And hopefully that'll make sense. So always anti, and with that anti configuration, obviously it's going to be trans, and you're going to have an enantiomer formation. So that's crazy. All right, so last thing on our list, and the book, for whatever reason, doesn't give a mechanism or a lot of in-depth details on the mechanism. So we'll go ahead and break this down into two steps. There's a hydroboration, and then there's an oxidation step. So let's just talk about hydroboration. And I'll go ahead and over here in white, I'll draw the overall reaction. There. It's a pi bond. I don't know if you can tell that or not, but we have BH3. First step. Second step is going to be H2O2 and an OH minus. But in the end result, think about this. What we get is the end result of this reaction is what you would consider a hydration reaction. And we'll go into depth on why and how this crazy process works. Okay, so first thing that we have here is, and BH3 is not something that I'm familiar with. It's not something that this book really talks much about, but again, we start off with an alkene, we're adding something. H, B, H2, it could be R2, we don't really care, but this boron is electron deficient, is I guess the point that I'm trying to make here. And so I'll go ahead and I'm going to draw it in red. I know I've kind of switched up with my electron pushing arrows. It's weird because this pi bond is going to go into the boron. It's going to be attracted to the boron. It's that electron deficient boron, even though it's an exception to the octet rule and kind of goofy. This boron here senses, it says, oh no, I'm starting to become positive. I better give off my electron, a bonded lone pair of hydrogen attached to it. And so it's going to be attracted to that kind of region, kind of in the same context of what we were talking about, that strained three-membered ring formation here. But it doesn't the point that I'm making is that there's not a carbocation being formed there. No carbocation, which is going to make our stereochemistry a lot easier. So the next step in this reaction here is we have this little structure drawn out there with the hydrogen there, and then a BH2. And then by some magical reaction, this is where the oxidation part comes in. By some magical reaction, we're going to, I guess, it's really frustrating to me because the book doesn't say much of what happens, but we're just going to go ahead and draw the next step in this reaction being right here. We have the H2O2 and then the OH minus. And your end product is going to be, and I'll go ahead and just draw it in blue. End product of this reaction is H. That hasn't really moved much. It's the BH2 is going to be replaced by this OH here. OH. So your book doesn't give you the mechanism. The book doesn't give me the mechanism. The purpose of this? What is the reasoning for this? This is the same thing as a hydration reaction, as adding as an acid catalyzed reaction that we had talked about earlier. And so the reason that we do this, as opposed to hydration, if you'll go back and look in your notes, you'll see that when we talked about hydration reaction, or any basically non-nucleophilic, it goes to the most substituted. In this, though, this is the only way, if you're talking about making stuff, to put an OH group on the, and this is, I probably should have explained, probably should have drawn this instead of just drawing it as a straight cycloalkane. I should have probably added some substitution in there on the substituted carbon. On the least substituted carbon. That's the only way we can do that. Another thing that's kind of unique about this, so that's the first thing that's really significant of it, and that it has syn geometry. They're on the same side, so I'm going to go ahead and just, throw in some wedges there. It's syn geometry every time. Why that works, how that works, book doesn't say, but that's another one of the significant things behind this reaction. And then the last one that's really, I guess, significant, yeah, we have no carbocation formation that I'm aware of. We have no rearrangements. So I'm just going to say no rearrangements. That's not as important as the fact that it will retains the stereochemistry. And what I mean by that is, and I'll go ahead and, if that's kind of related to the syn thing, is that this is a syn addition. And then the replacement of the BH2 with the OH, or the BR2 with the OH, is also a syn geometry. But we have a hydroxide group put on the least substituted carbon, that's so counterintuitive to what we've learned in the past.